Okay, so I was just talking about why the expectation here has t, even though if you look at our budget constraint, uh, excuse me, our lifetime utility function, we're maximizing at e0. Well, the reason why is because we get to re-optimize. So you can imagine somebody living their life, each period taking t as given, they get to re-optimize their ct plus 1. They don't have to fix that at the beginning of their lives. So, so of course, if we're thinking about our expected lifetime utility, then it has to be our expectation from time zero. But if we're thinking about actually optimizing and decisions about optimizing, then all that somebody has to think about, well, what I should say is that when you're thinking about what's going to happen at time t plus 1, you already know what happened at time t. You're allowed to readjust. So that's why this expression here has a expectation at time t in it, because we're allowed to readjust. Okay, so that's kind of it. So in the general case, we can't really solve this model if we want to answer the question like how does the economy respond to shocks. You saw that that we even have a hard time simulating the neoclassical growth model. So this model, where we have can have all sorts of crazy shocks to technology and government purchases, you could imagine that this model is much, much more difficult to solve. People's decisions are going to change when there's a shock. So the basic idea in this literature is to use an approach called log linearization around the balanced growth path. And then to sort of just use Taylor approximations to these things that we have already solved. So let me just scroll up again. So just make an approximation, a log linear approximation of this expression relating consumption to leisure. That's actually not too bad, because you could just say log consumption is equal to, put the t's in, is equal to log wages divided by b, if you like, minus log 1 minus LT. We're not quite there because you can see that we have this log of 1 minus LT rather than log of LT. But you get something that looks like that. So that's a log linearization. You can see that this is almost linear in logs in terms of the relationship between CT and LT. Not quite because of this 1 minus. And then you could do something similar up here. If you take logs, you can see that this will become linear. There will be a linear relationship between CT plus 1 and CT. Of course, it's complicated because we still have this issue that we can't separate these components. Also, it's not a super, I'm not going to get too much into this here, but the log of the integral is not equal to the integral of the log. So it means that this equation is somewhat more challenging to log linearize. So there's much more in the book. I'm not going to actually go through it too much in class. I'll maybe talk a little bit through my appendix slides here about how you'd actually solve this model. But basically what we're going to do is we're going to use something called the method of undetermined coefficients. Let me actually scroll up here. Okay, I don't really say much about it here. But the idea here is that we've got these state variables which are endogenous. So we've got some history that led us to a KT. We've got some history that led us to an AT, that's the technology shock, and then some government T. And then our consumption today is going to be, again, this is all in logs, and deviations from the balanced growth path is going to be related to deviations of these three variables from the balanced growth path. These are like the state variables. And the same is true for labor. It's going to be related to log linearly related to deviations from these three variables. Okay, so using that approximation, we can also get capital T plus 1, again, as a function of these variables. By the way, these are, again, this little tilde. I didn't ever say this, but K tilde means deviations KT from balanced growth path. So that's not super exact. I've got it more exactly in the appendix, but you just want to think about these as deviations where the balanced growth path is 0, but whatever. So deviations at KT plus 1 are going to be related to deviations at KT, deviations at of AT and GT. So once you have this equation, then that's going to actually help us a lot. If we knew what BKK was, BKA was, and BKG was, we can actually do quite a bit with this model because this is going to link period T to period T plus 1. So for instance, we know how labor evolves. That's exogenous by assumption. We know how AT evolves. That's an exogenous process that we as sort of, when we're simulating an economy, we're sort of God. So we can decide what this AT is. We can decide what GT is. And then, agents sort of take each capital level that they inherit as given. Once we know this, we can sort of turn the crank and sort of just iterate this economy forward, figuring out how production will change. And then since we have a relationship between production and consumption and leisure through these equations, right? This is giving us a relationship between capital and consumption. Here's capital and leisure. Once we combine these three things, we can think about sort of the path. And again, since output is just labor combined with A combined with capital, we'll be able to figure out what is the deviations of output from its steady state level. If there's a shock to AT, we'll be able to figure out what's the deviation of consumption from its steady state level if there's a shock to AT, and we'll be able to figure out what's the response of labor to a shock to AT as well. And that's kind of the point, right? That's what we want to figure out. How do these exogenous changes, stochastic changes, random changes to AT around its balanced growth path, how is that going to affect output and consumption and labor? And can we make that, can we design a model, or have we designed a model that's going to match major moments of the data? So that's what we're going to do next. I'll do that in another video.